Hello there, welcome to another astronomy remote learning lesson. We're still in Unit 1 and we're going to be looking at the things you can see on the screen today, so 1.4 and 1.5. So we're going to look at the latitude and longitude coordinate system, and then we're going to look at these points on the Earth, what they mean. So the equator, Tropic of Cancer, Tropic of Capricorn, Arctic Circle, Antarctic Circle, Prime Meridian, North Pole and South Pole. So let's get to it. This is where it fits in with the whole of topic 1. So there is another remote learning lesson which is based on 1.1, 1.2 and 1.3. So today 1.4, 1.5 as I said. So this is the Earth, and the first term that we're going to get to grips with is the equator. You probably know it, you know what it means. Maybe you don't know the exact meaning of the word, but it is a line that splits the Earth in two. So equator comes from Latin term meaning equal, so it splits the Earth into two equal parts, a northern half and a southern half. And you can see that that's called the northern hemisphere and the southern hemisphere. Now hemi is a word that could be translated into meaning half. So we've got the northern half sphere and the southern half sphere. We live in the northern hemisphere, obviously, and directly above the equator, and as far as you can get from the equator, north and south, we call that the North Pole and the South Pole. And that's based on the axis that the Earth rotates around, and we'll see the relevance of that when we do tilt the Earth. Okay, so that's the equator. Now, if the Earth had no tilt, then the Sun would always be directly above the equator. So by that I mean that if you stood on the equator and looked directly up in the sky, as far away from the ground as you could, you would see the Sun. Don't look at the Sun, it will damage your eyes. If you were here, if you looked directly up, you'd look that way, so you'd have to look at an angle to the Sun. So the only place you'd ever have the Sun directly above and there would be casting no shadow would be on the equator. We wouldn't have any seasons. The equator would always be the hottest point, and it would get gradually cooler as we went further away from the equator, because the Sun's rays would be hitting at an angle, so technically you'll be receiving fewer of the Sun's rays. But as you probably know, the Earth is tilted on an axis, so we'll have a look at that now. Here we go, and I've added in the tilt of the Earth, and I've also added in the rotation of the Earth around the Sun and some interesting distances. So sometimes people have the misconception that it's hotter in summer because we're closer to the Sun, which actually there's a certain amount of logic to it. The Sun is the heat source, so you would think the closer we get, the hotter it gets. But actually a change of about 5 million kilometers is not going to change the temperature any noticeable amount. But there is a time when we're close to the Sun, and it's in January, believe it or not. So, you know, in the freezing cold of January, it probably doesn't feel like we're close to the Sun. And then when we're furthest away, it tends to be July. These terms translate as well. Peri would translate from Latin as near, and ap translates to away from. Now, Helios is an old god of the sun. It's a Greek god of the sun. So Helio, that's where it comes from, Helios. The Roman god of sun is Sol, which is where solar comes from. Okay, so near sun is perihelion, and away from sun is aphelion. Ap, away. And peri means near. Peri's got 4 letters in, and near's got 4 letters in. So, you know, a slight difference, and there is a term that comes up quite a bit, which is called 1 astronomical unit, which you don't need to note this down now. We'll do that in a later topic. But an astronomical unit, otherwise known as an AU, is 150 million kilometers. So we don't need to quote how far away the Sun is at every separate day, because it does change. But the average distance from the Earth to the Sun is 150 million kilometers. That's 1 AU. Okay, but here you can also see that it's tilted. So here in July, the northern hemisphere, can we see, is tilted towards the Sun, and in January the southern hemisphere is tilted towards the Sun. So the closer you tilt towards the sun, the more of the sun's rays you catch and the hotter it will be. But that also means, I suppose, the equator is not so special at the moment, is it? So in January, the equator's up here, and it's this point here that's getting most of the sun's rays. And that is relevant. And we'll look at that in a second. Okay, so it's the tilt of the Earth that causes the seasons. So let's get to grips with how that changes. This is a bit fast for my eyes, I'll be honest, but you can pause the video and try and capture it in one position. So when it's on the right hand side, so if this was a clock, 3 o'clock, that would be summer for the northern hemisphere. It's tilted towards, northern hemisphere is tilted towards the sun. When it's on the left, so at 9 o'clock, the green line, or the southern hemisphere, is tilted towards the sun. So that's their summer. But the reason I put this up is to try and get to grips with 12 o'clock and 6 o'clock. So at the very top and the very bottom of this rotation, maybe you'll be able to work out that it's actually the equator that's tilted most towards the sun. Because, I mean, it's hard to talk about left and right on this, a two-dimensional screen. But yeah, the axis of rotation is not towards or away from the sun. It's side on to the sun at the top and the bottom. So kind of the equator has two times when it's getting most of the sun's rays, at the very top and at the very bottom. So this is like a capture of something very similar here. So we've got summer for the northern hemisphere. This is halfway between. So technically the equator is getting most of the sun's rays. So if I go back here, if we're calling this on average the 21st of June, we'd have this 21st of September, and this is the 21st of December, which is the peak of the summer in the southern hemisphere. Okay, and then just going back here, it just shows an example of when we're not going to be thinking about the sun at different angles. It's directly above the equator, so you would cast no shadow on the equator. Okay, so the terms then. So this is the peak of the summer in the southern hemisphere, and this is the lowest you could go, or the furthest you could go away from the equator at any time and have the sun directly above you. You would be here, you'd look directly up towards the sun, and you would cast no shadow, so you could see the sun directly above you. So that line is special, and that line notes the lowest point that the sun reaches to be directly above it, and that's called the Tropic of Capricorn. 6 months later, this is the highest the sun gets in relation to away from the equator, and that's the Tropic of Capricorn. And the areas in between the Tropic of Capricorn and the Tropic of Cancer, just referred to sometimes as the tropics. So you talk about tropical weather. It tends to have like a dry season and a rainy season instead of the 4 seasons that we're used to. So that would be the December solstice, or for us the winter solstice, and here is the June solstice, or the summer solstice as we would refer to it. Up here, as I keep going on about, this is the point where 3 months in between each one, the sun would be directly above the equator, and that's the spring or vernal equinox, and then 3 months on, and then another 3 months you're down here, and that will be the autumnal equinox. Okay? So, here they are. So we've got the Tropic of Cancer and the Tropic of Capricorn. So if you had to explain it, this would be a good way to do it, I suppose, and maybe I would probably jot these down as your notes. Now, we're going to move on to the 2 circles. So you've got the Arctic Circle and the Antarctic Circle. There is a funny, and I'll watch this video now. I'd encourage you to watch this video. It's a very short video, but it just shows the eerie places on the Earth where you might have 24 hours of darkness or 24 hours of light. Now that wouldn't happen if the sun didn't, if the Earth, wasn't tilted on an axis. Everything would get its fair share of sun. But there's times when you're tilted away and you just will never ever get some sun. So if we go back here and we can see that, if this, you just rotate this Earth, so the sun's over here to the right, rotate this Earth around a full day, and you'll notice this point here, the South Pole, it will never get any sunlight at all. It's always going to be in the same position. The Earth rotates around the poles, so this point won't move essentially, so you just 24 hours of darkness. But actually you can see, if we go up to the Antarctic Circle, you can see that this plate will just rotate around here, and it will stay in the darkness. It will stay in the half of the Earth that's away from the sun. So anywhere below the Antarctic Circle could have 24 hours of darkness. Now the Arctic Circle, the other way, you can see at this point here, at the peak of the summer, in the northern hemisphere, gets 24 hours of sunlight. So, you know, obviously 6 months later they'll swap over. The Arctic Circle will get 24 hours of darkness, and the Antarctic Circle 24 hours of sunlight. So here's your notes here really, which explain that pretty straightforward, I would say. So at 66.5 degrees north of the equator, you've got the Arctic Circle. Do have a look at that video. I'll hopefully attach the PowerPoint. And then, of course, the southern example of that is the Antarctic Circle. Okay, and the Antarctic Circle is 66, well, more accurately 0.33 degrees south of the equator. Okay, so you just think of it as the point that gets 24 hours of sunlight at some point, or 24 hours of darkness. Anywhere more north of the Antarctic Circle or more south of the Arctic Circle will never ever have 24 hours of sunlight or darkness. So I suppose this is a little summary. It wouldn't hurt to copy this diagram. So this is the winter solstice, 21st December, but you can see the points marked on here. I don't think they're going to ask you for the exact position of the Arctic Circle, but they could do it in a multi-choice, I suppose. And then these are latitude measurements, which I'll talk about in a second. Okay, so you've got all the points measured on there. Right, and then the other thing that we need to go through is latitude and longitude. So what we've done is we had this line that we made up called the equator, which split the Earth in two, and then we decided to just keep splitting it, keep having these horizontal lines that cut across the Earth all the way up to the very North Pole and all the way up to the very South Pole. But we kind of did it like by measuring the angle. So if you're at this center of the Earth and you look out to the equator, we'd call that 0 degrees. But if you look directly up, that would be 90 degrees. So that's how we've split it. So you'll find we go 10, 20, 30, 40, 50, 60, 70, 80, 90 degrees north, and then the South Pole is 90 degrees south. 0 degrees would just be on the equator. So there are two 90 degrees, north and south. Latitude, the lines are lateral. They go across. Longitude looks a bit like a chocolate orange, and longitude go the other way, so that they go from North Pole to South Pole, every line. But there wasn't an obvious starting point for longitude. It was obvious that we just start latitude in the middle at the equator, but where did we start longitude? So we decided to start it at the prime meridian, and there's a term that you need to understand. And aren't we lucky? You can see the prime meridian goes through Britain. And here's a bit of history. 1884. So before that, to measure longitude, people were using different starting points. So in 1884 it was decided to use Greenwich. The Greenwich meridian was chosen. So that's our starting point. So if you are in Greenwich, you are at 0 degrees longitude. And here we go. So it does look like a chocolate orange, but here's Greenwich, funny looking Great Britain there, and then we can go east or west from Greenwich. So if we go east all the way here, but you can see that in Britain you're not going to go more than about 4 degrees west. But you will go all the way around. So if we're doing it in degrees, just imagine a protractor. If you go halfway around, that's 180 degrees. So you can go as far as 180 degrees west and as far as 180 degrees east. 180 degrees west and 180 degrees east are both the same point. Though here it is kind of flattened out a bit for you. Okay, so aren't we lucky to have the prime meridian in our country? You can go and see a line in Greenwich. It's a nice thing to do. And here it is, cut open the chocolate orange, and you can see the angles inside. Okay. Now this leads on to the need for time zones as well, but we're not doing that in this presentation. Okay, and here's the latitude lines shown a bit more clearly. So you go all the way up to 90 degrees north of the North Pole, and there it is, cut open as well. Okay, so there's a link to a video here which will explain latitude and longitude. 2 videos actually, and they're nice, and I'll put the links on, as I said, and I will add this PowerPoint as well. And then I'll finish by just talking about the poles, the polar regions. So I suppose the first couple of slides kind of showed the poles. It's just the point 90 degrees north of the equator or 90 degrees south of the equator. It's the point that the imaginary axis of the Earth seems to go through. It's the area that we rotate around. But it is a bit more complex than that, I suppose, and this is mostly just for fun. But the most interesting part of this is, obviously we're referring to a geographical North Pole, which is relating to the area that we rotate around, and the axis of rotation goes through. But there's also magnetic relevance, isn't there? So there's the North Pole, magnetic North Pole, and the magnetic South Pole. Now, if you ever thought, which way does a North Pole get attracted? So a North Pole is attracted to a South Pole. North and North repel, if you can remember Year 8 magnetism. So North is attracted to South. So if you have the North Pole of a compass, that's not attracted to a North Pole of an Earth. It's attracted to a South Pole of an Earth. So what we call the geographic North Pole, and we do refer to it as the magnetic North Pole, is actually a South Pole. And it's something that makes perfect sense once you get told it, but it's probably a question you've never really asked. Okay, so that is it. Just to summarise, we've looked at latitude and longitude, and then hopefully you can understand the terms equator, Tropic of Capricorn, Tropic of Cancer, Antarctic Circle, Arctic Circle, Prime Meridian, North Pole and South Pole. And there will be a couple of worksheets just to help consolidate this knowledge attached on class charts as well. Okay, thank you.